Despite widespread pledges and the declining costs of renewable energy, the math on our current trajectory points to a clear outcome. Global emissions are not falling fast enough to prevent warming from overshooting the 2 degrees Celsius threshold. Because mitigation efforts are lagging, the scientific community is now being forced to evaluate an entirely different class of response, broadly known as climate intervention, or geoengineering. Interventions fall into a strict two-part taxonomy. The first factor is carbon dioxide removal, or CDR. This treats the root chemical cause of warming by extracting greenhouse gases directly out of the atmosphere. While CDR is the safest approach, the technology to sequester carbon is currently too slow and unproven to deploy at the scale required to stop near-term temperature spikes. That brings us to the second vector, solar radiation management, or SRM. Instead of removing carbon, SRM treats the thermodynamic symptom. It reflects a portion of incoming shortwave solar energy back into space before it can heat the Earth. Because carbon removal cannot act fast enough, SRM is rapidly gaining traction among policy analysts as a viable, fast-acting alternative. It shifts the entire climate debate from a problem of chemistry to a problem of radiation. To understand SRM, we have to look at the specific physical mechanism it relies on, planetary albedo, which is simply the measure of a surface's reflectivity. This chart from the Royal Society illustrates albedo feedback loops between the biosphere and surface temperatures, using the Daisy World model. The principle is straightforward. Increasing the reflectivity of the planet's surface or atmosphere means Earth absorbs less solar radiation and the system cools. This directly counters the anthropogenic greenhouse effect. While greenhouse gases trap outgoing long-wave thermal radiation, albedo prevents incoming short-wave radiation from entering the system in the first place. The specific goal of stratospheric SRM is to artificially increase Earth's atmospheric albedo, just enough to mathematically cancel out the exact amount of heat being trapped by excess greenhouse gases. Altering the Earth's albedo sidesteps the carbon problem entirely. It provides a theoretical pathway to lower global temperatures without actually repairing the damaged atmosphere. Stratospheric aerosol injection is not a speculative concept. We know the physics work because the Earth performs this exact experiment on a regular basis. Large-scale volcanic eruptions provide the primary observational baseline for how injected sulfur behaves in the upper atmosphere. When the Raikkoke volcano erupted in 2019, it punched straight through the lower cloud deck. That eruption emitted roughly 1.4 teragrams of sulfur dioxide into the stratosphere, where the gas quickly converted into sulfate aerosols. Once suspended, these microscopic sulfate aerosols act as tiny mirrors. They scatter and reflect incoming shortwave radiation back to space, measurably cooling the surface below. This cooling effect lasts because the stratosphere behaves very differently than the weather systems we experience. Low-altitude rain clouds wash out in a matter of days, but aerosols injected into the highly stable stratosphere persist for a year or more. By studying these natural events, engineers realized that preventing a near-term temperature overshoot could be achieved by building a continuous synthetic volcano. To translate that physics into a concrete engineering project, we have to define the target. To offset an aggressive warming overshoot, we would need to achieve a radiative forcing of -2 watts per square meter. Hitting that target requires an immense volume of material. We would need to inject roughly 12 teragrams, or 12 million tons, of sulfur into the stratosphere every single year. This diagram outlines the proposed delivery mechanisms for lofting that massive payload into the upper atmosphere, ranging from ships and trains to towers, balloons, and aircraft. Ground-based methods, like firing artillery shells or pumping gas up a tremendously tall tower, have been evaluated and dismissed. They are simply too logistically inefficient to maintain a 12 teragram annual payload. Airborne delivery is the viable route, but we cannot retrofit current commercial planes to fly that high with Hercow. Achieving this requires fleets of newly designed, high-altitude autonomous aircraft. The estimated cost to design, build, and operate this autonomous fleet ranges from $20 billion to $200 billion annually. In the context of global GDP, a $200 billion price tag is a modest sum. A single mid-sized nation or a small coalition of countries could unilaterally afford to cool the entire planet. but climate models show that this low cost is deceptive. The immediate benefit of a global temperature drop comes with severe, cascading secondary effects. Because SRM only blocks sunlight and does not remove a single molecule of CO2, the severe ecological crisis of ocean acidification continues to accelerate completely unabated. There are also direct chemical risks. Injecting millions of tons of sulfur into the upper atmosphere is predicted to accelerate the depletion of the stratospheric ozone layer. Then there are the regional disparities. While the global average temperature drops, the artificial albedo shield disrupts regional precipitation patterns. Current models indicate it could severely alter monsoon cycles, particularly across Africa and Asia. The low cost of SRM is an illusion. It merely trades a global heating crisis for a highly complex, unevenly distributed ecological crisis that we do not fully understand. This graph illustrates John Shepard's napkin diagram. It shows a temperature curve rising above a critical threshold, with SRM used to shave off the peak. SRM is a temporary stopgap, capping the warming while mitigation and carbon dioxide removal slowly lower atmospheric carbon underneath. Relying on SRM without aggressively removing carbon introduces a specific risk, a scenario known as termination shock. If the sulfur injection fleet is suddenly halted by economic collapse, sabotage, or war, the artificial cooling vanishes immediately, while trapped greenhouse gases remain. The physical result is a violent, rapid spike in global temperatures. The warming suppressed over decades would hit the Earth in months, moving so fast it outpaces human or ecological adaptation. Implementing SRM puts the entire planet on a life support system. Once turned on, it cannot be safely unplugged until the underlying carbon is completely removed. This brings us to the consensus reached by the Royal Society and geoengineering researchers. The primary hurdle of climate intervention is no longer engineering, it is governance. Because the technology is cheap and accessible, it presents an acute geopolitical danger. One rogue nation could deploy an aerosol shield to protect its own agricultural output, while simultaneously causing a severe drought in a neighboring country. We are comparing the rapid, precise pace of aeronautics engineering with the historical sluggishness and gridlock of international climate treaties. Currently, there is no international regulatory framework or treaty equipped to manage transboundary geoengineering experiments, let alone full-scale deployment. The scientific community has outlined a strict mandate. No large-scale outdoor SRM deployment should ever occur without unprecedented global consensus and a fully funded parallel exit strategy in the form of carbon removal. We have the physical capability to engineer a cooler planet, but relying on SRM as a backup plan is a geopolitical trap. It is a distraction from the necessity of leaving fossil fuels in the ground.